So you can ignore what my wife said at the beginning of the last video. She just doesn't know what the hell she's talking about. So anyway, in this example, we have an equation for diffraction, d sine theta equals m lambda, and you want to use, in part A, use that equation to show how you can get the approximation for xm. So, just to give you a little diagram of it, you have a beam of light that's being shined through a couple slits. So let's say the slits are right here. The beam of light, if it goes straight ahead onto the screen, we're going to say that total distance is L. So there's going to be a central point of brightness, and then a little bit further up you might have a point of brightness, and that distance from there to there is xm. In this case it would be x1 because that's the first bright spot. And then, so the angle we're talking about is the angle going from here to where that bright spot is to form that bright spot. So this angle in here is the theta. So the equation that we start out with for diffraction is d sine of theta is equal to m lambda. But if you look at this triangle, with this right here being the right angle, you can see that we know the opposite side of the triangle from this angle, and we know the adjacent side. Well, that doesn't help if there's a sine theta in there, because if you know the opposite and the adjacent, that's using a tangent. But what we can do is, we can say that sine of theta is approximately equal to, and this only works for small angles, and that's why we're showing this derivation for when the angle is small, the sine of theta is approximately equal to, it's going to be the opposite side, which is the xm, over, now we know that it's over the hypotenuse, but if you look at this side of the triangle, the hypotenuse, versus this side of the triangle, they're almost the same length. We know that the hypotenuse is going to be slightly longer, but these are so close together in length that we can just, in place of the hypotenuse, we can do the adjacent side, which is L. So since the sine of theta is approximately equal to xm over L, we can take this and replace it in that sine of theta. So we now have d xm over L is approximately equal to m lambda. And if you solve this equation for xm, you get xm is approximately equal to m lambda L over d. For part B, show how you would find the angle in the first equation if that angle is not small. So let's say we have something where the case looks kind of like this. You have that horizontal part, but then the angle is significantly bigger. So you have the xm there and the L right there. So now, since this side of the triangle is not approximately equal to this side, we have to find the theta by using the inverse tangent, since we know the opposite side and the adjacent side. So we can say that theta equals the inverse tangent of opposite side xm over the adjacent side L, and that will give you the angle theta, which you could then take and plug into this equation. So that's all you have to do to find theta. And for part C, it says determine the standard unit for the variable m in these equations. So let's just take either one of those equations. It doesn't really matter which one. I'll just say d sine of theta is equal to m lambda. Well, sine of theta doesn't have units. Theta has units of degrees, but when you take the sine of that, it doesn't have units. So we can basically x that part of the equation out in terms of the units and just focus on the units of the d and the lambda. If I rearrange what's left in the equation, m is equal to d over lambda. The d is a distance, so that has standard units of meters, and the lambda is also a distance because it's a wavelength, so that has standard units of meters. So since we have length divided by length, or if you put units in there, meters divided by meters, it would cancel out, and you would just see that m has no units. which should make sense because m is just an integer representing the spot number from the central spot.